Hi guys, this video is going out a little bit earlier, which is good. What has motivated me to put out a video a little bit earlier on YouTube? Well, a conference on video games in the classroom that I'm going to on Thursday. So you guys should have plenty of time to watch this by Friday, which probably won't do, no, let me back up. We probably will do a video quiz on Friday that will count as a homework grade, as every other video quiz has, over this stuff. Okay, so at this point, this will be posted around the time some of you guys are still watching the rest of the Chapter 23 videos. We've seen a lot of sampling distributions. We've seen a sampling distribution for one proportion. We've seen a confidence interval for one proportion. We have done a hypothesis test for one proportion. We have done a sampling distribution for one mean way back in Chapter 18, and then we paused until we looked at the t-distribution again, and we introduced the t-distribution in Chapter 23. The t-distribution allowed us to talk about confidence intervals and hypothesis tests for single means. So we've seen those recently. We've done confidence intervals and hypothesis tests for differences between means as well. So we've done for between proportions as well. What we're going to do today in Chapter 24, we're going to use the t-distribution to talk about a confidence interval for the difference between two different sample means. Now obviously the t-distribution is going to be used automatically for means when we want to build a confidence interval, because remember, confidence intervals always, 100% of the time, go from sample information to trying to estimate population information, which means if you just have sample information, that the normal bell curve is not an option for you when you're talking about these confidence intervals for means, because you've only got sample data to play with. All right, let's go ahead and read the problem that we've got. This hopefully won't be too terribly long. Hope to knock this out in about 20 minutes. Stats student designed an experiment to test battery life. To estimate the difference between mean lifetimes of generic and brand name batteries, he kept a battery-powered CD player continuously playing the same CD with the volume control fixed at 5. And he measured the time until no more music was heard through the headphones. All right, he's got measurements of the lifetimes in minutes of 6 generic and 6 brand name AA batteries from a randomized experiment. We want to find an interval that is likely with 95% confidence to contain the true difference between the mean lifetime of the generic brand AA batteries and the mean lifetime of the brand name batteries. So, if you recall, let me go back to the past real quick here in green. We saw a confidence interval for the difference between two proportions looking something like this. P hat 1 minus P hat 2 plus or minus the critical z-score times, remember, not standard error pooled, that was the pooled standard error was for hypothesis testing, times the standard error of P hat 1 minus P hat 2. Well, thankfully, so we've seen that in the past, thankfully the confidence interval for the difference between means rather than for proportions looks a heck of a lot similar, heck of a lot like the same. We've got y bar 1 minus y bar 2 plus or minus, instead of a z-score, because we've got sample data to work with these means, we're using the t-distribution and thus a t-score here times the standard error of y bar 1 minus y bar 2. All right. Where you might, some of you guys might see here real quick that if we're talking about two different samples worth of data, we've got two different sample sizes to play with. So what the heck do we do to get the degrees of freedom to find our critical t-value from our 95% confidence? Well, there's good and bad here. And the good definitely outweighs the bad. The bad is that the degrees of freedom formula is very complex. The good is that you never have to use it. Let me show you how complex it would be to find the degrees of freedom for this confidence interval, given that you've got two different samples worth of data. You wouldn't simply add the 6 and the 6 to get degrees of freedom equal to 12 minus 1. Instead, if you were to calculate this by hand, you would find those circled degrees of freedom for a confidence interval with the following formula. probably need all this space right here. df equal to, in parentheses in the numerator, the standard deviation of the first sample squared over sample size of the first sample here, plus standard deviation of the second sample squared over the second sample size, all of that in parentheses squared, over, big old denominator here, 1 over n1 minus 1, first sample size, subtract off 1, that's degrees of freedom for that single sample, times standard deviation of the first squared over sample size of the first, all of that squared, plus 1 over second sample size minus 1 times second standard deviation squared over the second sample size, all of that squared. That is the formula you would have to use to define the degrees of freedom for this confidence interval for the difference between two means. But you don't have to do that because there's a calculator function that allows you to get that degrees of freedom very quickly. And you're not missing out on anything for the AP exam. They're not going to ask you to calculate by hand the degrees of freedom for a confidence interval for the difference between means. Again, you have full reign of the calculator in the AP exam. So let's go ahead and, if that's our template underlined right here, let's go ahead and see what we can do to get that confidence interval. First, we need to make note of conditions. From the confidence interval for a single mean, we really have only one additional condition to check. Remember, confidence interval for a single mean, check the following three things. Randomization, as always, 10% condition is the sample size less than 10% of the population size. And third thing, the nearly normal condition, we're still checking those three things. The additional one here, of the 4 conditions, we've got one additional, and that is the independent groups assumption. Independent groups assumption. We have used that condition before. Off the top of my head, I don't remember. I think we used that when we were trying to build bell curves for discrete random variables that independently followed normal models. So it's been a while, but we've seen this condition actually come up. Basically, all this is asking is whether or not these two different sample sizes could have affected each other in any way based upon how we collected the data. Well, if you think about it, when I get 6 batteries that are generic and 6 batteries that are brand name, I'm buying those 6 batteries in packaging that is separate from each other, manufactured separately from each other. So really, this is an easy one to knock out. Let's go ahead and say that yes, my 6 generic, my 6 brand name are independent groups because the batteries come from separate companies purchased in separate containers. Ergo, therefore, the groups are independent. Okay, first condition knocked out, and that's the new condition. After that, let's check randomization. We were told, let's see, we were told the batteries were obtained in a randomized way. We're given that information. Given that the batteries are random, randomized. Okay, second condition knocked out, not a big deal. Third condition next up, 10%. Certainly 6 generic and 6 brand name are both less than 10% of all generics and 10% of all brand name batteries. Okay, well, brand names standing for brand name batteries. Okay, we want to next check the nearly normal condition here, which we're going to do that. Yeah, kind of a pain in the butt. It doesn't take us too long though. Once you get the data entered into lists here, nearly normal condition. Let's do that in blue. That's kind of the funky one. Don't forget about it. Because we've got two different samples here, we need to build two histograms to make sure that both the brand name and the generic data is unimodal and symmetric. Remember, as we talked about last time, to meet the nearly normal condition, it really depends upon your sample size. Because we've got a sample size of 6 generics and a sample size of 6 brand names, you need both of these histograms to be unimodal and symmetric. Now, the caveat with that is that when you build your histograms, you've got a lot of flexibility in terms of your bin sizes and your view window and all that sort of thing. So as long as you can build a histogram, with these 6 sample data for generic and brand name, that is unimodal and symmetric, use it. Even if the first histogram you build doesn't happen to be those two things, try again, see if you can force it to be those two things, and then the nearly normal condition will still be met. So, nearly normal condition, we're knocking out. Okay, and let me go ahead and show you what I did here to meet these two conditions on Wabbit. Let me turn this sucker on. Let me go Stat, Edit, and let me scroll back up. Set this up earlier. Let me just double check that the data looks good. I see 194, 2055, 199.2, 172.4, 184, 169.5. Brand name looks good. And generic 197, 2035, 2035, 2065, 222.5, and 2094. Okay, that looks good. So let's go ahead and check the brand name data first. That's my L1. We'll go Stat Plot. That's on. Check it to, or change it to L2 here. Second list. Did I say change it to L2? I meant change it to L1. I'd been working with L2. We've got the histogram selected. That looks good. Let's see what by default zoom. Let me quit out of that. Zoom stat. The data looks like. Okay, so we've got these 5 bins. No, as of right now, we have not met the unimodal and symmetric condition for nearly normal. So let's go ahead and change the X scale a little bit. Let's see what the window conditions are set up to right now. They've set the X min to 169.5, so pretty close to 170, and the X max to almost 215. I found, by playing around with this, that if we change the X min to 160, bump it down just a little bit, change the X max to 220, so we're bumping that up just a tad. We're making, wait, let's see, I don't need to change. Let me quit out of that. Window, we'll leave it. Okay, let's change the X scale instead. It's currently at 9, that's awfully small. We had, if you were to check out the graph and trace across, you've got bins with only 1 data value in them, with a count of 1. So those bins could be smashed together a little bit better. Let's go back to window. Let's change the X scale to 20, and Y max, let's, for the sake of safety here, so we can make sure that the tops of the bins are in the window, let's bump that up to 4. Let's see if that gets the job done. Let's graph this. And there we go. We've got, yeah, that's what worked out for me. Trace this, and we're going to reproduce the histogram on paper here. We've got the 3 bins, counts of 3, 2, and 1, and we certainly have unimodality. We've more or less got symmetry. I mean, as close as you're going to get with 6 data values, and 3 of them being in the center bin. The best you can do is 2 to one side and 1 to the other. So we've got that. All right, so let's reproduce that below here. My histogram showing the distribution of brand name battery life looks as follows. You've got counts of 1, 2, 3. So you've got your frequency, or counts, on the vertical axis. You've got your battery life at 160 minutes, and then 180, 200, 220. This is 200. Battery life for brand name. Okay, and we said, I think it was 2, 3, and 1. So we've got first bin set up as follows, second and the third. little sloppy, but still, we're just meeting the conditions. There's your brand name histogram. So yeah, we've met unimodality and symmetry there. Let's go ahead and go back to the graphing calculator here. We'll go to second stat plot. Plot 1's still on. We've got a histogram. We're going to change this list to L2. Enter there. Zoom. Oh, it keeps doing that to me. Zoom stat. Okay, and again, they're wanting to give us 5 bins. If we check out window, the X scale is just under 8. And the data for the generic batteries is spread from 190, give or take, to 225-ish. So I think we can do better for the bin sizes. Let's see if instead of an X scale, a bin width of 7.95, let's double that, more or less. Let's go to 15. Let's change the X min. Let's drop it down just a tad to 180. Just playing around here. And the X max, if we're going with bin sizes of 15, 180 plus a multiple of 15, you can add 15, 30, 45, 60, etc. to the X max. Let's change that to 225, so we're adding 45, 3 times that 15, that bin width. We're going to change the maximum height of the bin, just for the sake of safety again, to 4, so we can capture all the bin heights. And let's graph that and see how it does. And wow, that's definitely going to get the job done there. We've got counts of 1, 4, and 1. So for the generic data, we've got a histogram that looks unimodal and symmetric. We will copy that down here below. Okay, so again, vertical axis is frequency. 1, 2, 3, 4. And your bins are set up at 180, 195, 210, 225. 210 we have right here. We've got the battery life in minutes for the generics. Okay, so bins at heights of 1, 4, and 1. Okay, all right. So it is not enough with the nearly normal condition to just build the histograms. Go ahead and say yes. Both distributions are unimodal and symmetric. So the NNC, the nearly normal condition, is met. Okay. All right. So all the conditions are knocked out. Yeah, clearly in blue, that's the condition that takes the most time. The new one again was the independent groups assumption for this 2 sample confidence interval for the means. Conditions are knocked out. Let's go to the mechanics. We'll go back to red for this. Mechanics. So we need, based upon the template that we saw above, this y bar 1 minus y bar 2 plus or minus t sub df times the standard error of y bar 1 minus y bar 2. Let's go ahead and talk about, let's write that below so we can have a visual reference here. Y bar 1 minus y bar 2 plus or minus t sub df, where we said the degrees of freedom we'll get from a calculator function instead of using that nasty equation that I showed you above, times the standard error of the difference between those sample means. Okay, let's talk about what we know. We have been given, or we know at this point, n sub g, the sample size of the generic batteries is 6, which is the same as the sample size of the brand name batteries. Y bar, the sample mean of the generics, is equal to 206.0. Now how do we get that? Let me show you again here, guys. To get the sample mean along with the sample standard deviation for any list of data, let me quit out of this right here. We're going to go stat, calc, 1 variable stats, or 1 var stats. L1 was my brand name, just double checking, yep. Brand name data here. Frequency list you don't have to worry about. We can calculate this, and there you go. X bar, or y bar, whichever you want to use. It doesn't really matter. As long as you've got a bar on a lowercase variable, you're referring to some sample data's mean. So y bar sub g is generics, and I ran it for the brand name, didn't I? Well, to get the sample mean for the generics, we would go second quit here, stat calc one variable stats on. Instead of L1, we will choose L2. That's where my generic data is kept. Frequency list, don't worry about, calculate that. And there you go, 206.0 for the generic mean. And the generic standard deviation is 10.3 here. Okay, so let's copy this data down that we have. Standard deviation of the generics was 10.3. Mean of the brand name was equal to 187.4. And last but not least, standard deviation of the brand name, sample standard deviation of the brand name, 14.6. Okay. All right, so the standard error calculation for this confidence interval is something that looks fairly familiar. Y bar sub g minus, so we're building, if we're using y bar sub g minus y bar sub b, generics minus brand name, and we're building the confidence interval such that it is generic minus brand name. So if this difference comes out to be positive for our confidence interval, if our confidence interval is a positive confidence interval, then the generics are outperforming, according to our samples, the brand name. If this difference for the confidence interval comes out to be negative, then the brand name is outperforming the generic batteries. So the standard error of this is equal to square root of standard deviation, sample standard deviation of the generics squared over their sample size plus standard deviation, sample standard deviation of the brand name squared over their sample size. Cap off the radical. So we're plugging in this radical we have 10.3 squared over 6 plus 14.6 squared over 6, which comes out to be 7.29. Okay, we'll circle that. That's the first thing that we need for right here. Okay, we'll get the, well, let's go ahead and mention what the difference in the sample means is real quick. So y bar sub g minus y bar sub b is equal to 206.0 minus 187.4, which comes out to be 18.6. Okay, so we've got that. Now, how do we get the critical t-score here? Well, first of all, notice that you need that degrees of freedom. To find the degrees of freedom, we're going to go to it is second distribution. Nope. Let's see, stat tests, and we're going to go to the two sample t interval, because we've got two different samples and we're using a t interval for means. Two sample t interval here it asks for your input as data or stats. Well, we've got the data listed in L1 and L2, so that's exactly what we want. With L1 and L2 already given, the frequencies, you don't have to worry about those. Confidence level looks good. That's at 0.95. They asked at the beginning of the problem that we use a confidence level here of 95%, so we're going to go with that. This is not pooled. Don't worry about that. We may not talk about pooling for confidence interval for two sample means because it's such a rare thing that you would have to do, and most of the time you don't want to do that. So we'll calculate this, and we find the degrees of freedom equal to 8.98. Nice thing about using this calculator function, which again was in stat tests down at the two sample t interval, nice thing about this is that the you don't have to use what is it called, inverse t, to find your critical t value. It gives you not only the degrees of freedom, 8.98. Oh, sorry, I'm not speaking correctly here. It does give you the degrees of freedom. We still have to use inverse t. My mistake. So 2 sample t interval. We set all that up with L1, L2, 0.95 for the confidence interval. Calculate that. And again, that was 8.98 for the degrees of freedom. Okay. So this circled piece right here is equal to 8.98. Now we need that critical t-score. That's the last piece of the problem that we are still out on. Well, let's go to the t-distribution where this confidence interval is centered, and we know that the degrees of freedom is equal to 8.98. We want 95% confidence, so we are going to use inverse t here on your calculator at, well, what percent of the data is less than this upper fence? You've got 2.5% to the left of that 95% window. So we're going to use 0.975 and specify your degrees of freedom, which is a non-integer number. That's okay. 8.98. And that gives you, I'll show you again on Wabbit here. Go to stat, calc, second distribution. I get those two confused a lot. Inverse t of 0.975 looks good. 8.98. I found 8.99 earlier. We will paste that, enter, and you have critical t-score of 2.263. Okay. 2.263. So that's the final piece of the puzzle circled right here. All right, so let's fill all this in together so we get the confidence interval for the true difference in battery life average between generics and brand names. We had, the first thing circled was 18.6 plus or minus. Our t-score was 2.263 right here times our standard error of 7.29 times 7.29. Okay, so again, this is your margin of error. Your confidence interval is centered here. That's the mean of the confidence interval, the 18.6. And then you're going this margin of error to the right and this margin of error to the left of this mean right here to get your entire window to capture the true mean difference between generics and brand names. Or if you convert this to sort of a coordinate pair style interval here, you've got between 2.1 and 35.1 minutes. That is to say, with 95% confidence, we believe that generics are lasting 2.1 to 35.1 minutes longer on average. That's kind of remarkable. All right, so let's write that conclusion out. Conclusion, I am 95% confident that the interval from 2.1 to 35.1 minutes captures the mean amount of time that generics outlast brand name batteries. Okay, and there you go. So again, looking back up here at the template for the confidence interval between two different means, looks super similar to the confidence interval for the difference between two proportions. It's used very similarly. The only trick here is finding your degrees of freedom, which we use. It was the 2 sample t interval to get the degrees of freedom for that test. All right, that's your video for the day. Have a good one, guys.